Hello everyone, this is me giving you a quick overview of your BC Calculus booster block poster project for T1. We are looking at some creative way of combining both optimization and related rates, two of the classic applications of your calculus skills. I will not read this all for you. I just want to emphasize that you really have a lot of freedom when you somehow combine optimization and related rates. So you can scheme your schemes and dream your dreams and come up with some crazy scenario whereby those things are somehow related. I don't want to give you a list of 20 things because I think it's fun to kind of come up with something on your own, but I've just got 3 here. The classic sliding ladder going down a wall where the top and the bottom are changing at different rates. You can somehow pick some point at which you do that classic problem and then also solve for when the area trapped underneath the ladder and created by the side of the building and the ground would be at a maximum. Now this one happens to have a sort of a symmetrical solution that is maybe not so interesting. That's why I don't mind kind of using it up. But maybe there's a variation on that that's a little bit more interesting. This is quite complicated. It's similar to one of the videos I produced where you're talking about like the angle created by goalposts in kicking a field goal, same concept. A camera moving along the sideline of a soccer match, filming the goal mouth. When you're right at the end line, it would be just 2 lined up posts and no area. As you back away, you see increasing area, but then as you get farther away, it diminishes in your horizon, so it gets smaller again. There's some optimal point, and you could find the rate at which you're moving relative to the distant goal mouth from the trolley that the camera is on. And then I am going to do this one as my example problem. The swimmer offshore needs to get to a point along a beach, and I'll go into that in a moment. Hopefully this will take you around 2 hours. We'll spend some time in class. Maybe there's a 15% tip thrown in there, but please don't go crazy. You could spend hours and hours and hours on this, and that is not the point. Try to create one quick problem that somehow unites these two. I have a template Google drawing for you to start on. You can drag and drop clip art, drag and drop screenshots, drag and drop photographs of your handwritten work, okay? And then do bring a version of your problem that does not have the solution on it so we can challenge each other in class in the final day presentation. Okay, so here is the grading rubric. It's pretty straightforward. It's 50 points. I do give you a chance for some extra credit with humor, creativity, and some sort of flair that you bring to your project. So have fun, enjoy that. Can't promise a ton of points, but you know, it might be something. Again, I'll let you read that. I'm not going to read through that. Here's my example. All right. Whoops, here is my example. I'm going to try to get this positioned a little bit more clearly. All right, here we go. Hopefully that is showing. Oops. There we go. So in this, you've got some swimmer, maybe it's SpongeBob, I don't know, swimming off the beach and stung by a jellyfish. If the swimmer is 100 meters from the shoreline measured perpendicularly, and there's 300 meters along the beach to the first aid station where you want to get some relief, where should you aim to get there as quickly as possible? Given that the swimmer can swim at 1.25 meters per second, I looked that up online. That's a reasonably fast swimming pace, not Olympic, but good. And then a running pace of about 2.5 meters per second, dragging that stung foot. How is it possible to minimize the time it takes you to get to first aid? Okay, so I've actually done this in 2 ways just to show off my skills. One is by aiming for a point X and doing some Pythagoras to get you there. Another is by aiming at an angle theta to get you there. You can read this on your own time, but like I said, I want you to present the problem and show a solution. And then I want you to somehow tie in a related rate problem. So the second part of my challenge is that at the halfway point of the swim, what is the change in absolute, as the crow flies distance, related to the rate that you are swimming? Okay, so that involves some good math. It's a law of cosines problem. Again, this is way more complicated than you necessarily have to be, but I just did this for fun and to show you the possibilities. So like I said, try to have some fun with this, create, somehow tie them together, bring in clip art and screenshots. And again, you do not have to do this on the computer. I just did that for clarity. You can handwrite your solutions and then snap a photo. That would definitely be faster. If you're curious about using Google to help you with the equations, you'll see that if you just go up under Insert, if you go to get your cursor somewhere in a blank page, Insert an equation, you then will see these tools up here, and so you can click on a square root if you want, and you can type in what you're doing. If you want to put an exponent, there's a good shortcut. That's a shift and then the 6, and you'll get an exponent up there. That gives you the shift and caret, and you can type in your exponent. I just typed these in. I also did some word processing, and then I just did screenshots of those. Okay, so that's the basics. I hope that helps. Good luck, everyone.